Yes, yes.
All right, hi everyone. Thanks for joining. It's a real pleasure to introduce Hanna here today. Hanna is a professor at University of Washington Computer Science and one of the senior directors at AI2. She's done a lot of work in a lot of exciting work in NLP and has really been moving a lot of her work also to generative AI and LLM training. I think many of us have a lot to thank her for because she's been really pushing a lot of the open source efforts at AI2. We're going to hear about more of that today, and both for academia and I think even industry, just seeing open source training, what people do, and be able to discuss things with an end-to-end pipeline, I think it's tremendous value. She's been doing a lot of work in reasoning for science, I know now too. She's a friend and a former colleague who has that at UW, and it's kind of a shame we didn't interact more then because I think a lot of our interests are.
Thank you. Thanks, Sham, for the introduction and inviting me. Thanks. Is the mic, does it sound okay?
Yeah.
Okay. Today I'm going to be talking about some of our most recent efforts in pre-training and post-training language models and I mostly talk about our most recent release, OLMo 3, which we released at the end of last year. Okay. I'm sure we tested it and it was working. So now, can you? I don't know why the. So now why? I want to push click and this is open. Oh, good. Okay, perfect. So. Good. So before I start, I want to talk a little bit about my journey in AI. It kind of resonates with a lot of things that we are seeing and how the field has evolved over time. So I started my first project in AI through my PhD, where I was working on symbolic reasoning and logical reasoning problems. Then I moved to NLP, where my first paper was actually to design a system that can solve arithmetic word problems. So I intentionally copied that problem here just to see how simple those types of problems that we could solve back then. And still, I think none of the systems were able to solve them. And we were one of the earliest working on how to learn to solve math problems. So then we realized the domain is still constrained, and then I moved on to doing a more generic question answering using deep learning back then. And then again, okay, what if we generalize it, look at more unified question answering system that can only do question answering, but in a wide range of tasks. Started working on generalizing things in like, okay, now why just answering question? Let's do instruction following. So this kind of, this is how the field was also evolving over time. But now look at the thinking model that we currently have that I pretty much queried OLMo on to solve this math problem, this competition problem, and it was able to solve it. So still, this is like a 7 billion parameter model. We know the bigger model can do more and more, but this is kind of how it is very interesting to see that in this period of almost 10 years, that paper was from 2014, how much the field has improved. Okay. So with this, I want to argue that now AI is everywhere, like we are seeing it in like a lot of applications, in real world applications and so on and so forth. But still, there are many fundamental challenges that need to be resolved. Okay, so I will give you some examples. We have really good reasoning agents, but I don't believe we have fully solved a lot of reasoning challenges yet, right? So what happens if we get to a new domain? Like we are hearing a lot about continual learning, test time, like all those things, right? how we solve and address these problems when the problem gets more and more complex. We need to rethink data paradigms. In the student discussion today, I mentioned we are getting out of really good high quality data, okay? But there are a lot of data that is private and proprietary, but like we cannot build and train these base models, these pre-trained models on that data, right? Because they are proprietary. But they exist. So what if we rethink our training paradigm such that on demand, we could kind of adapt to those private data? We need to be able to use AI across other domains. I know in Kempner, you guys are working a lot with neuroscientists and so on to kind of help make these bridges, but we need to do more of this. And it is very important to kind of think of how we apply these algorithms, or can they be applied out of the box in other domains? Most likely no, but then what is next? How we can extend these algorithms? And then finally, one thing that is very important is being able to make them more efficient, more compact, more personalized, such that we have all of us have our LLMs in our laptops, and start kind of making these personalized AI models. So these are like some fundamental challenges that all of us as a community need to be working on. Okay. But for that, I want to argue that we are seeing a lot of model releases, but these models that we work with, either through API or like at the end of the whole post-training stages, we use, like everybody, when they releases their model, it's just like the final snapshot of this whole complicated process, okay? What I argue is we need something that we kind of coined this term model flow, which is we need to have access to the full development of this whole training process, because when we want to push for some of these capabilities, we need to kind of interfere at different stages. And I argue this is very important to be able to do on-demand customization. So this is kind of our pitch here, and we have tried to release this whole model flow through our OLMo project. We think with this, we are empowering the infinite customization through many changes that people can do through model development cycle. Importantly, not just by a few companies who can work on these model developments, but the whole research community can start integrating and working on these different stages. And through this, we really love the community to be able to inspect our models, to customize, to evaluate, and even innovate, see what is next, how we can make improvements. Also, we showed how the process works, right? We show that with very careful data curation, training recipes, and so on, we are able to match or sometimes exceed the proprietary or some models that they are just open rate. And again, this is very important. When we have access to the data, then the whole community can start doing innovations and work together. So we've done and we've released different types of models across pre-training, post-training, and multimodal. Today, I'm going to be mostly talking about our recent findings in pre-training and post-training. Okay, so we have released different variants of OLMo and my team has started working on this since 2023. It's like with this motivation that we have a team. They are all working on separate stages of language model training. What if we put all these efforts together, build one model? Obviously, we will publish less, but hopefully the outcome will be more impactful. And then suddenly we got some GPUs from AMD. Sham also offered us some Kempner GPUs back then, I remember. So through this, we started training OLMo. Now, when I think back, the model was not good at all, but we learned a lot through this process. All the way up to OLMo 3, which we released last year, which now we have 7 billion parameter and 32 billion parameter model. Okay, so this is the snapshot of our most recent model. So here, every point in this figure represent the results at the end of our training stages, like pre-training, mid-training, adding long context, and then different stages of post-training. And then we compare it when models are available. For example, basically our competitors were OLMo models, were Quen models back then, which we had for Quen 2, we had the final stage of pre-training and the final stage of post-training, which we compared. But Quen 3, unfortunately, the only final model is at the end of the post-training stages. So that was this is kind of how you could look at different stages of training and how you could build this model. So it was very exciting to see that in terms of in the evaluation set, like I kept repeating today, that evaluation data sets really matter. But in the evaluation set that we were comparing with, our model is almost on par with Quen 3 at the last stage. Okay, so now in this talk, I want to go into how we did pre-training and post-training. And the big goal that we were pushing for OLMo 3 was how to make OLMo able to think. Okay, so how to add these how to make OLMo capable of doing better reasoning, like solving these type of more complex math problems, coding capabilities, and so on. Because based on what we study, we realized, okay, OLMo 2 is far from other models in doing this type of tests. And this is kind of how I want to explain our journey here. So by the way, if you want to like interrupt me and ask me questions, so I'm going to talk about many different stages. Feel free to interrupt. Okay, but first, many thanks to the whole OLMo team and our collaborators. I'm sure I'm missing some faces here, but we worked a lot with a lot of people in academia and industry to help us build this model. Okay, so OLMo model flow, it has base training and post-training. During base training, we included these 3 stages: pre-training, mid-training, and long context. I'm going to talk about how this works, but it's mostly like changing the type of data that we were using for training. And post-training, it has supervised fine-tuning, preference tuning, and reinforcement learning. It has different types of data and different types of algorithms and how we kind of improve our model. So each of these stages has a very tight loop between improving the model, making sure we have good evaluations, as good as we can, and making sure that we curate data, collect data to address and make us good in those evaluations. Okay, so why reasoning tasks are more complex? Okay, so as we get more and look at more and more complex tasks, we face this problem that it is much harder to collect data, okay? So for example, for reasoning tasks, we need longer chain of thought to tell us how the model kind of thinks to address these queries, but how to collect this data? Expert annotation is very expensive, just crude distillation is noisy, right? So we need to come up with a good way of how to curate this data, okay? And again, that is not enough. Maybe we need to also think of how to think of different algorithmic paradigms or how we can integrate and introduce different, for example, reward signals on evaluating these models. Okay, so this was kind of our opening. So, but particularly, let's look at what challenges did we face at different stages of training in OLMo. In pre-training, when we started thinking back and look at OLMo 2 training data, we realized that almost 95% of our data are web crawls, okay? Definitely not suitable for reasoning tasks, okay? But now the question is, obviously we need to add more data, more diverse data, like we need to add code, math, STEM type data, and so on. But then what is the filtering algorithm here? And what is the ideal way to mix them, right? How do I decide these proportions? So this is a very important question. Long context, obviously, when we are looking at these reasoning traces, we need to improve our long context reasoning. There were some published work in the literature, and we thought we immediately applied them. Obviously, we did, and they didn't work, like the data that was available and so on. So then understanding what is the problem, like what type of data we need. Do we see some negative interferences between the architectures that we are using and the long context capability? So we needed to do a lot of study there. And obviously how we scale up training, because long context transformers, obviously training is getting more and more expensive. So a lot of infra and engineering work also was required. So when we get to mid-training and post-training, which means that we need higher quality data, now the bottleneck is data is very expensive. So how we add this type of data? Two, when we add this data, are we losing other capabilities, and how we could compensate for that? Finally, it was, we know reinforcement learning is very important. We know reinforcement learning is very expensive and costly. So how we could scale up RL? Is it algorithmic? Is it infra? Like how we could solve those problems? The other very important kind of global challenges, we are compute, but we have a compute bottleneck, right? So we need to be very efficient and careful in our experimentation, right? So we need to optimize quality versus cost to figure out how we get really good results with minimum amount of GPU. And we need to do a lot of kind of prior and pre-analysis to figure out how to solve this problem. And this was also a really big challenge. How do we outperform or get close to even open weight models? We don't know their training data, right? So and like we want to make sure that we do all the correct things in like decontamination and everything to make sure that the gains are real. Okay. So how did we start this? So a few, like this was actually very important for us, because we needed to, like there were some research questions, right? We had a big team, but it was very hard to kind of understand which problems are more important and which problems would scale up. So the way we kind of decided, we worked was this iterative refinement process. Decided on what capabilities we want to improve, make sure we have evaluation sets in place, and then make sure these evaluation sets can be carried across different stages of training, right? So I know I want to improve on math and reasoning tasks. I need to know what type of initial evaluation settings give me signals so that it makes me to get good results at the end of post-training. Obviously, if I bring a very complex math reasoning benchmark during pre-training, there is no way I could get early signal, okay? Also, it's very important to think like all of them as a concert, right? So this is what I mean by customization need to happen throughout different stages of training, not just at the final stage. One other thing was we decided to focus on this terminology of innovation execution balance, that we need to push to solve some research problems, but at the same time, it's kind of like very similar to the RL setting, exploration, exploitation. At some point, we decided, okay, that's enough. We need to add them to the infra. Now it's getting to some sort of engineering to make sure everything can be integrated together. Also, at the end of the day, we pushed for scientific findings and kind of be very kind of science-driven. If we make a decision, we need to justify it. Why we are making this decision, like we should see it in our results, or like and so on. Okay, so now let's start a pre-training process. So first principle, optimize quality versus cost. In order to get here, we need to do some things before pre-training time and during pre-training. Okay. How do we do that? We need to define shared standards such that different teams who are working on different capabilities, they could compare results with each other, and shared infra, and then build scaling laws such that in a cheap way, you could figure out which of these new additions show improvement, okay? And during the pre-training run, we made sure that we are improving our training infra such that training has the highest throughput as much as we can, and then we make sure our training is stable. Okay, so here what we did was the more evaluation sets and benchmark you look at, the more capabilities your model would have, okay? So we started looking at more than 100 academic benchmarks that were available to us. and I started analyzing them to see we had a few lines of papers on understanding which of them show us some good signal into discriminating good models versus bad models, which of these data sets are noisy versus the others, and then can we cluster these evaluation benchmarks? Like these evaluation benchmarks all kind of show similar types of capability. So we worked a lot on these such that we could think of a few metrics that we are trying to optimize at a smaller scale. Okay, and this is kind of something that we push for, which is we are looking for benchmarks that show high signal and have low noise. Okay, so we optimize for something for signal to noise ratio. For example, ARC challenge, we figured out is a good benchmark. Okay, it generally shows us some good signal early on and less noisy. And the behavior is like interestingly kind of scales when the model size grows. Math, this is very interesting. We know we want to have some good results at the end of the day on Minerva math, okay? But then at very small scale, it's meaningless to evaluate on Minerva math, okay? So how could we come up with better metrics that shows a good signal toward math? So we did a few things here. We first generated, like I'm not going into the details, we first generated a few synthetic data sets to evaluate general math capabilities. This was a step one. Step two is kind of the literature has also shown, which is push for other metrics like bit per byte type metrics rather than the final accuracy. And we noticed that it's actually really useful. Okay. So training stability is also very important. So this is one of our earliest runs from OLMo models that we saw some loss spikes and particularly grad norm spikes at the beginning during the training. We thought it is fine. Let's see what happens. But then at some point, we couldn't make any progress afterwards. And whatever intervention we did later in the training, the loss diverged. Okay, so we made sure that afterwards we really need to focus on having a stable training run. And after at that stage, we never saw improvement over our benchmark. We need to improve our training infrastructure. So here is, for example, how our throughput looks like now. We went all the way from 750 tokens per second to more than 10,000 tokens per second. We did the same thing in this version of OLMo to improve our RL infra that enabled almost 4 times, 5 times faster in RL, which enabled us kind of make more progress in the reasoning test. Okay, so this is mostly very, very quick kind of explanation what things helped us improve. We realized that initialization surprisingly mattered in stabilizing our training run. Like, for example, that run that I showed you, it was like the initialization was bad. And then we made sure to add some normalizations, like layer norms, QK norms, adding Z-loss and so on. Those also help us to stabilize the training. In order to improve training throughput, obviously, when you increase batch size, it's really good. But you don't want to increase it so much, right? So there were studies in the critical batch size on what is the best batch size that you could use to speed up training. We actually did some theoretical analysis to figure out what is that best batch size. And interestingly, we found that once we figured that out for 1 billion parameter model, it actually scales to 7B. So those were a few kind of on the side analysis projects that we did to figure out some of these improvements. Okay, so now I want to move on to data, which I also discussed with a lot of people this morning, that data is really, really important. So once you have a stable model, you are halfway there. Like the changes that you would make are important, but if you have bad data, there is no way you could recover. So we need to really push hard on improving data quality. Okay. So how do we do that? We start with web data, common crawl, a lot of documents, a lot of noise. We started doing deduplication, and through this process, we started to kind of remove a lot of the data this way. So it is very important to do as much deduplication as you can, because then you could push to repeat higher quality data more rather than like having some low quality data there. Another step that was very helpful for this round of OLMo for us was to come up with fine-grained categorization of the data over the web. Okay, so we had some kind of side paper with one of our interns that helped, like Alex Wettig, who helped us to kind of build this topic and domain classifier on the web data. This was critical for us to do better mixing of the data. Okay, and then finally we use this to do data mixing and quality of sample. But why this data mixing is important? Okay, so let's go back to this. So you would say, if I want to have, like intuitively, if I want to have higher quality reasoning models, I probably should upsample my stem type data, right? But how much, right? So these are like intuition versus kind of really figuring out and solving the optimization problem. This is kind of the big question that we are asking here. So the very quick summary, this is basically how we did it. We try to figure out what is the smallest size model that we could train a model to show some signal on the metric that we are optimizing, particularly this BPB metric that I just talked about. And then we randomly generate a bunch of these mixes, okay? And run, this is called swarms, and then for every X, now we can calculate the metric, okay? So we ran a lot of these. Okay, and now we have Y versus X for all of these points, and then solve this optimization problem. Like I'm a little bit simplifying. Okay, so it had some constraints and so on, but tell me what is the best mix that overall gives me the best metric. Okay, and this is how I'm solving this minimization problem. And through this process, this is the final kind of we have done it at 2 stages. One is finding the mix for the web data, and then and then for each of these data, so like for code, for math, like ran this mixing algorithm for each of these, and then on the final mix. Okay, so we ran this multiple times at different stages. And as we were expecting, like for example, here you see the orange one, like this is the blue is the normal distribution, like the natural distribution that you would imagine someone would use. But then the orange one are the one that our method has optimized for. And intuitively, as you would expect, it has selected more on the like math and science technology type data. Okay, good. So any question on this? Yes.
How consistent is the mixture that you find at I thought it was like 30 N, so the small scale, how consistent is it like sort of like larger?
That was exactly the question. So we started, like a lot of our effort was spent to find that size. So we had some 1B results, like we had trained 1B result with kind of some heuristic mix. Okay, and then we started from like a smallest scale, and then we gradually increased that to figure out what is a good swarm size. That was exactly like a lot of our analysis, like a lot of our time was spent on finding that ideal size actually for us. That was exactly the question. And again, we did this. Actually, I want to jump into this right now. Again, we did this for mid-training. So let me tell you what I mean by mid-training first, and I will tell you how we apply mixing algorithm here. So I've had this discussion with a lot of people today, which is it is very hard to figure out what is an ideal curriculum to introduce data for pre-training, okay? Because it is expensive, like there are multiple schools of thought. Maybe you should start with higher quality data, then bring in general data, then end with higher quality data. Or like start with general data, then end with higher quality data, and then continue, okay? So we did this second regime, and admittedly, we haven't compared with the first regime. So to us, the way we have done was bringing general data up to like 7 trillion token, 6 trillion token. And then after that, kind of give really compact, very high quality data to the model, that helps us be good in the type of benchmarks that we are trying to optimize for, okay? So this is kind of our recipe. And for that process, we included some of our original high quality original data. This is like common crawl, and obviously much less of that. And then very carefully curated high quality data, okay? In total, I think we've used 50 billion tokens, but we tried a little bit larger. We didn't see much more gain, so we stick with 50 billion token, okay? But the way we generated this, we allow to use synthetic data paradigms to generate this. And we did a bunch of tricks, like please refer to the OLMo paper. I'm not talking about all the details, but we made sure we have some instruction type data, we have some question answering data, we have math reasoning tracer. So it's kind of, people call it cold start, or I don't know, warm start, the reasoning process for the RL. So we introduced some of these here. Okay. And again, the process here was, I wanna emphasize on this process, our methodology here, because it was a little bit messy. We need to generate this data. You evaluate, all of them show signals, but at the same time, we did multiple integration tests to make sure that when we put these things together, we don't see negative interference. Because here, it's like they are competing for tokens, right? So this type of data are competing for tokens. So it's very important to do these gradual integration tests.
Yes. Like, how do you think about what high quality data is? Like we think about math or something, like you can do data mixtures, but like when we try things like with fine web, it's like taking the subset that's like good makes a very big difference.
Yeah.
Yeah. There they just asked.
Yeah.
Educational. That was like good enough to get like a very good filter.
Actually, I don't call that yet high quality, because fine web is mostly only collected from web. Yes. Like if you see only math data from web, I wouldn't call it high quality. Like maybe what I mean is more like natural looking data, which you could find it through web. That's what I call through pre-training. In mid-training, I am intentionally curating data to become good in some capabilities that I'm interested in.
How do you? So I think the only point for fine web, it seemed like the filtering. Like I'm agreeing with the point that the filtering of like math data is like very important.
Very important. I agree.
And how do you?
Yeah, like this is actually a part of it is here in like some of this. But let me give you an example. By high quality, like still that fine web data doesn't have those. Maybe high quality is not a correct term, like targeted data. Let's call it targeted data. Like we know we need to do long chain of thought reasoning, okay? But those fine web data, or like that math data that I can find in fine web, probably don't have much of those long chain of thought reasoning data, okay? So here I'm intentionally curating some long chain reasoning data. So we started thinking about what type of reasoning queries are there, and then started kind of come up with some kind of hierarchy of the type of reason. These were manual effort, reasoning effort.
You want to change, but then how did you find the change? Did you?
Okay, that's why I say I'm allowing synthetic data. We curated it with like some of like DeepSeek, for example, model, and then filter the lower quality one. We assumed we have access to some model that is able to generate chain of thought data. This is the big assumption. I would argue if I want to do it like in an ideal way, I will use experts to annotate some chain of thought data for me. Yes.
So I'm just trying to understand so you first do pre-training, you do like a warm-up, and then you like a post indicate, and then mid-training is a phase that comes after this?
Yes.
Oh, so like, and what do you do with the scheduler again? Like, is it just like warm-up?
Exactly, yeah.
Okay, so have you tried like integrating the mid-training data like the training stage?
So yeah, I had this discussion with someone today. By principle, we don't want to include this synthetic data in our pre-training. We want our pre-training, like in my pre-training research, I don't want to have this assumption that I have access to something like DeepSeek. Why it? Because it's like 50 billion token. I can like remove it later on, replace it. But if it is mixed in my whole pre-training data, I don't want to like redesign all my pre-training data that way. So it's more like academic type understanding here. Yeah, but that's the 100% a valid question. Yeah, cool. And some of it by default is there. Like some of these chain of thought type data are there, but it's like naturally occurring. I'm not intentionally putting there. But this is something we are experimenting now. Okay, good. So then we ran our mixing algorithm again here. To your question, it took us a long time to figure out what is the smallest unit of mixing that shows, a smallest size model and data that shows good signal to the final outcome. Once we figured it out, then we again run our mixing algorithm. Okay, good. So long context training, it's actually, I mentioned about challenges that we would face during long context training. And I named them. The big question was having access to high quality data, okay? Most of the data that we find on the web, it's like super short, like 4,000 tokens or so. But now when we want to do long context, at least you want to get to 32,000 tokens, 64,000 tokens, and so on. If you crudely concatenating them together, still it's not as high quality and you won't see that much of the gain. But one thing we observed was PDFs, scientific PDFs particularly, consist of really high quality scientific data that you could use, okay? But how do we linearize scientific PDF was the big challenge we were facing. So obvious idea, let's linearize it, we use one of the GPT versions back then to linearize it for us. Did a really good job, but super expensive. I need trillions of tokens, but that's super expensive, doesn't work for us. So on the side, we actually created this thing called OLMo CR, where it's an OCR model that processes PDFs into kind of tokens for training and linearizes this. Again, when we did that, we were not sure if we are doing a good job or not. On the side, we curated this OLMo CR bench to evaluate it. And then after that, actually, like from last year to this year, we are seeing a lot of OCR models for this processing. So once it worked, then we managed to collect a lot of data, 1 trillion token. Now we are even collecting more data, which was a good help for us to have long context data. Yes.
Sorry to interrupt, but how does like what you talked about before generalize to like multimodal, like MoMo?
Yeah. Sorry, what was this?
Oh, all right. What you were talking about like this section before, all right, and I guess including this section, how does this generalize to like multimodal, like maybe MoMo?
Yeah, that's actually a very good question. So I don't have a concrete response to that, but it is ongoing. So intuitively, when you add some increase the capabilities of your models, like these reasoning capabilities, long context capabilities, and so like these generic capabilities, it's a better starting point for building multimodal model, okay? But that is not enough. We are right now discussing this with our multimodal team because we are seeing some obvious flaws from when we applied this and then just crudely did like post-training for the MoLMo. And now we are trying to understand what is this big capability that we are missing, or like what type of inherent capabilities we need to be added in the pre-training. I particularly don't, like we need to somehow integrate a spatial type information here, but at this time I don't have a good answer. Yeah, very good question. Like some of these are necessary, but not sufficient. I agree. Cool. Okay. Oh, besides that, we did a lot of studies here on how to curate this data and then kind of some architecture changes, which I'm not going to go into the detail. Okay, good. So open data helps us to do better traceability. And basically, it helps to, when the model generates an output, now we can kind of credit it back and then kind of trace it back to the training data. So I'm not arguing this model shows the causal reason of why this output is generated. Okay, so here is how it looks. We have a query like who is Celine Dion. We look at the generated output, but now we are able to find phrases that exist in the response back to the training data to argue potentially this has come from this, or if the model has seen these phrases or not. So this actually helps us to do better tracing of the model. So why this is challenging and why this is important? First, how do we do this kind of phrase matching to the pre-training data? We know it's like 5 trillion tokens or more. And it's very hard to be able to do this kind of fetching and search. So how did we do it? By thinking about kind of our data structure algorithm ideas of representing this this collection of tokens with suffix arrays. And this very much enabled us to do real-time search of finding phrases that are in our pre-training data. And then in our latest effort, we actually improved it, borrowing ideas from computational biology, built something called Infinigram Mini, which now is able to build and store even more gigantic data sets. We thought this was actually a very interesting use case of how to be able to look at this pre-training data and response and trace it back to pre-training data. Yes.
So just to clarify, the tracing is based on lexical similarity.
100%, yeah.
Functions or anything.
Yeah, no. One quick thing, a little bit of kind of TF-IDF type approach is also involved in terms of filtering the documents that are there, but mostly lexical phrasing. We are actually discussing of how to connect it with dense model, dense representation.
Yeah, I like the tracing. Just a quick question or request. I think now on your demo, it's only allowing to search for the outputs.
Yeah, not the reasoning tracer.
And if I have just a string and I want to find it in the training data, can I do that on your interface?
I think okay. So we have 2 demos. We might take that down, but in our initial version of Infinigram, we had it.
Oh, okay.
Maybe we have already taken this down.
Yeah.
Yeah.
Because that's
question.
very useful.
I know. I agree. It's a little bit expensive to serve those, but yeah, I agree. I can check. Thank you.
Thanks.
Yeah. Okay. So pause a little bit. So now I want to move on to the post-training efforts. And in post-training is actually where I want to get at something like this to be able to solve these complex math problems, for example, or more complex reasoning challenges. Again, we need to kind of look at this loop of eval, model, and data, which is like very much connected to each other. I've talked about the challenges. It's harder to get data this way, like for these complex challenges. And then, depending on how we curate and collect data, we need to adjust and optimize algorithms for them. Okay, so let's say how we did that. For SFT data, this is how we approached it. We started thinking about creative ways on how to kind of systematically, with the scaffolding approaches, to curate synthetic data for a bunch of these tasks. Okay, so if we just crudely use, for example, a GPT, like a very strong teacher model, to generate these reasoning traces, it won't work. So we needed to think of some creative ways to do that. I'm not going to talk about details. We also learned that preference data is very important. Preference data meaning that we say output for a given query, output A is preferred over output B. But how we collect annotation there, we came up with an interesting method. And then we focused a lot on improving RL here. Mostly, I'm going to talk about that. OK, so on preference tuning, we, based on one paper from our team, we actually noticed this is important, that preference tuning works when there is a significant difference between chosen responses and rejected responses, okay? But if chosen and rejected responses are both very high quality, very similar to each other, one is a little bit better, during preference tuning, the model won't capture this. So then we realized pushing on having more difference between these outputs actually gives us much more improvement during the preference tuning stage. Okay, so let me explain this a little bit more better. So let's say we are training OLMo. This is a student model. And let's say I'm using this teacher model, Quen 332B model. It's a bigger model. This is a 7B model, okay? If I generate thinking and reasoning traces from Quen 332B and then continue SFT on that data, I'm not getting improved score on some of the reasoning tests, okay? However, if I say, look at the difference between the output of Quen 332B and Quen 3.6B, which like heuristically and intuitively it should be much worse, then we started seeing a lot of improvement on some of the reasoning tasks that we saw. So intuitively, the way we are thinking is it is sharpening the distribution to be closer to the better output than the worse output, okay? So yes.
That's passive one.
Yes, yes.
I would assume like the passive key doesn't, or like for large.
Okay, this is actually a very good question. I don't have a good answer here, but here is the thing. We thought a lot about, okay, so this is the important observation, and we've seen it, we saw it many times. In order for RL to work, okay, we really needed to have a good starting point, okay? So for example, RL0, doing RL at the end of pre-training, we see really big jump, okay? However, it never gets to where you start with a better SFT. This for sure, like we know that. So then we did multiple analysis of what if I just start directly from SFT, directly go to my RL, or start from this preference tuning and then start my RL. This was better. Why it was better? Maybe you're right. Maybe top K doesn't matter. But the reason it mattered was DPO is kind of a little bit kind of make this jump start happen faster because it starts to kind of make the model already better in reasoning. And therefore, it kind of, RL is much more expensive than this offline training. So we felt like if we had more GPUs, probably RL would catch up, but this is a good starting point. That's a good option. Like maybe if we could let them train longer, they might get to each other, but we didn't get to that. At the beginning, they were definitely starting from DPO was better for us. Okay, or maybe it enables us have it less like K for GRPO. That's also possible. That is also possible. Okay. So RLVR. This is the last stage of training, which many of you know that it is important to bootstrap training. Okay. So the basic idea is prompts come in, the policy is getting updated, the response is generated, and then the environment provides some reward. Okay. So initially, a lot of people, when they were using rewards, many of you had heard about RLHF. This reward model was trying to tell us what, like for a given query, how I can score that chosen response is better than the rejected response, right? And then hence all the algorithms, PPO, DPO, and so on came into play, okay? So in our 2-3 paper, and then DeepSeek also came right after our paper, I'm pretty sure it was concurrent, we argued it this way. For some tasks, we actually could easily look at verification, okay? So we don't need to just look at the pairwise comparison. We could just, like for math problems, we know the problem could be solved or not, so we could just look at this verification reward, okay? And it worked. It was very much working, but then we were surprised. This is pretty much the basic RL idea, why people came up with that RLHF before this. Then we started applying the same algorithm to the earlier language models and realized the reason was earlier language models were not that good, so this never worked, okay? Now that language models have improved, so RLVR shows better signal even than RLHF. Okay, so this is the finding. So in our earliest work, we just focused on math pretty much. here for OLMo 3, we started defining all these verification signals and diversifying the domain, okay? So we looked at instruction following, which is the percentage of constraints that are satisfied. This is the verification. For code generation, we designed this synthetic environment that we could execute code. And then we defined the unit tests, mathematical reasoning, and general chat. We trained an LLM that could judge the quality of a response, okay? And then we collected data across all these domains. We had a specific reward. And this was actually very interesting to see. We pretty much started to optimize data in parallel. And then at the end of the day, combine them together. And it worked. We are very happy to see that it worked, because one of our ideas was to do sequential RL training on each of them. But fortunately, when we combine and let RL train, it worked, which was very satisfying. Okay. So we also realized offline filtering in our earlier experiment was very important. You don't need very easy problems. You don't need very hard problems. So we needed something in between to kind of make sure the RL works. Okay. So this is our experiment of showing that when we combine, look, okay, let me remind myself how the experiments look like. So this is the column shows the if-eval score, which is like instruction following benchmark, okay? The green shows the accuracy of the model when we combine all the data, okay? So as you see, the model increases its if-eval score, okay? Here on the right-hand side, you see alpaca eval score, which is like you could think of it as a proxy for chat capability, okay? When we look at the mixture, it stays as is, like RL didn't improve it much. But if I just use if-eval, like instruction following data, the chat capability decreased a lot, okay? So this was also another signal helping us that when we combine data, we didn't see this negative interference, which was really good and exciting. Okay. So now let me get a little bit into the details of the algorithm. Okay, and why RL infra is really important. So how does RL work? There are two groups of GPUs working with each other. One group that are inference GPUs that generate the rollouts of the RL, and then the other is like train, which they update the parameter, okay? And this is kind of the process. You send the prompt completions, the model gets updated, and then the new model generates the data. Okay, so LM inference is slow, especially when we deal with longer reasoning traces. Okay, so this is where generation happens. So this could be the process, right? So if we are thinking that they are fully asynchronous. So these GPUs are getting generated, then they would stay for some time, they would stay idle for some time, then training is happening, and then we pass it back to generation, and then now my training GPUs are idle. Absolutely awful, right? Because I'm wasting a lot of resources here. Okay. There is even a bigger problem, which it was a very big deal last year. The field is growing so fast. Now we have a solution. There is also, because of like the internals of GPUs and probably the way that VLLM is implemented, there is even some mismatch between the log probabilities generated by my inference step versus what my kind of transformer model has, okay? So there was a solution. We pretty much follow the solution from the literature to use importance sampling to kind of balance these ways. Okay, so this is good. But now let's think of when we are looking at long reasoning traces, okay? This is the realistic case is like this, right? So we are solving math problems. Some of them are easier, done. The generation is over. Some of them are really long. So like even some of the inference GPUs now are idle, okay? And then this happens, and then like the update, this is not much energy need to be spent. Okay. So how did we solve this problem? It was a lot of packing, making sure like distributed system type engineering. We made sure that GPUs don't stay idle. We made sure to pass the shorter sequence of at every minute, like the GPUs are generating. sometimes these are finished, sometimes not. When they are not finished, we store their values into KV cache and then restart at the next stage. Okay, so what is the downside? We're gonna be a little bit off policy, right? So here, see, not all of these generated. I'm doing my training, but over the time we realize it's actually working and it is fine, more efficient because it allows me to do more steps. Yes.
So in the other one, you're not that off policy. There's like different kernels, and then you get like slightly different numerics, and that already like not the fair training.
Exactly.
Here you're very off policy.
We are very off policy.
Like it doesn't fight.
It doesn't. It didn't like with the amount that we gain on RL efficiency, it like we gained a lot more. Because even though we were a little bit off policy, we were compared like we had the earliest implementation. We were looking at like our improvement accuracies. It was pretty much the same, but this was much faster. It enabled me to do more updates.
We're using an MOE.
No, no.
So you still found issues.
Yes.
How long?
I'm pretty sure when we switch to MOE, we will have a problem. There's more problems. I know, and that's why we are a little bit moving away from MOE. That's scary. I agree.
And how long was the generation when you started to have problems?
I don't exactly know. Remember what is it? What do you mean exactly?
How long was the generation?
Good question. We started with 32K, allowing every generation to go to 32K tokens. Then once we improved our RL infra, we started to 64K. Then we could even go longer.
So
in the previous case, 32K, yes. But then in this case, I think we moved to, I think the latest model was trained with 64K because I'm not waiting anymore.
Well, like the standard answer is typically much shorter.
Exactly.
That's pretty good.
Exactly. That's what I'm getting. Standard answers are much shorter, but some of them are longer, so I had to wait. Okay, good. So this is like, okay, I'm not gonna talk about this, but this is pretty much the original GRPO equation. And then this is us. We ablated a lot of choices that people started making in the last year, like DAPO, like a lot of these things. And this was kind of our final recommendation that these things all matter. And some of the changes that people were claiming matter, they did not actually. So some of them were like, okay, it was important to do that truncated importance sampling, clip higher, and so on. So this is kind of the final GRPO object. We call it modern kind of GRPO objective. It's not a very different variation of GRPO, but some of those design choices actually mattered, really. Okay, so now this is how it impacted us. Our earlier experiments in RL was super slow. When, for example, one of our runs took us 16 days to see the final convergence and see, okay, we are seeing the plateau. Our final run was like done in 5 days. And basically after all those changes, this is kind of how we started seeing progress much faster. There were a few other changes I didn't mention, which is active refilling of the data. That was also really important because when the mod policy gets improved, it now can solve more problems. So you don't want to add it to your training batch. So like kind of removing them and on demand add required example was very important. We are not wasting RL resources, like training resources here. Okay, good. Okay, so this was actually very interesting, which was when we released OLMo. Okay, I don't want you to read all these numbers, just look at the trend. So when we released OLMo, it was like end of November. We let the RL go, continue, and we still saw improvement over the period of like the next few weeks. And then we started seeing plateau. And again, we released OLMo 3.1, but like our numbers, a lot of reasoning numbers went higher, which was exciting to show that, okay, we could scale RL now. So again, this is the numbers, how it is compared to models like Qwen 3 32B. One thing I was very much proud of was we put a lot of emphasis in improving instruction following capabilities and then kind of making sure how it has been integrated into the RL stage. And basically, we didn't have much evaluation. Our only evaluation was this very much saturated if-eval benchmark. But then we had a held out set. Interestingly, we saw it was like growing over time when we ran it basically the last day, which showed instruction following capability really improved. Okay. So when we chat, I'm also happy to talk about while we were optimizing for these benchmarks, at some stage, we realized we are getting really, really high AMI scores, which is like this hard math challenging benchmark. Then we were about to kind of finalize the weights. We started doing some vibe testing, and the model was awful. It was doing a lot of weird chatting discussions and so on. We realized we obviously pushed a lot on these reasoning benchmarks, forget about chat capability. So it's like we had to retrain. We figured out the problems and so on, again, with balancing the data. But this is important. Like your model will get as good as the benchmarks that you are optimizing for. So it's really important to always have up-to-date benchmarks and improve based on the final queries. Okay. Good. Any questions? Okay. So I want to move on to one more project. Do we have time, actually? I can be quick on this.
Yeah.
Okay.
Just try to wrap up in 10 minutes.
Okay, sounds good. So then this is a big question, actually, which is, does RLVR actually work on a lot of different types of open-ended question answering, right? So the big assumption that RLVR has is I can verify it at the end of generation, okay? So in this project, we look at deep research type tasks, which is, it tries to target open-ended question answering. Okay. So what do I mean by deep research agents? You are using this in like current API models, which is it's asking me question like what are differences between OLMo 2 and OLMo 3? The model needs to keep kind of thinking and planning, search for resources, and then updating, reading papers, and then comparing, and then finally giving you results, right? So a lot of things are dynamic in this sense, right? And it is not just like, okay, what is the real good reward or good verification that I can use at the end, okay? And then the final summary. So now, deep research work exists in the literature, but most of the time, like the previous work, all of them look at deep research, but mostly focus on short form question answering. Why? Because it's like you have access to ground truth answers, and you could verify it, okay? Then again, you could apply the same RLVR approach, plan, reason, answer questions, and so on, but then finally verify if the final answer is correct or not, okay? But obviously, this doesn't work for when we have cases like this that, okay, I have this scientific question. What is the state of the art in this particular problem? The model can answer this, but like, can I understand if these sources are credible? Is it up-to-date information? Did I do a good job in citation? Like, obviously, you are seeing all these hallucinations and so on. Okay, so how did we look at this? We built this system called Dr. Tulu. It works on open-ended and long-form tasks. It is getting connected to search tools that have MCP servers. In particular, we are looking at scientific search algorithms. So we use Serper AI and Semantic Scholar scientific search. And then we also make sure kind of we evaluate citation and we provide this attribution. Okay. So how did we solve this problem? You probably also all thought about this, that we need to integrate rubrics, right? When we have these longer generated text, I need to come up with ways to kind of come up with metrics on how do I say this generated response is good or bad, okay? You could think of for like, let's say a scientific response, you could say, I want to make sure the citations are accurate, the generated response is concise, while it is organized, it is relevant to the topic, like a lot of these things, okay? So fortunately, through Semantic Scholar and our kind of collaborator, we had access to expert annotators. So we said, annotate these for us. We're going to use these rubrics for generating these and kind of my reinforcement learning method. So unfortunately, it didn't work out. Why? Because the model very quickly learned to hack those rubrics. And very quickly, we saw our model is significantly better than, for example, a cloud model that is designed to do this task. However, when we were looking at the output, they were not good, that good, okay? So it very quickly learned to hack these rubrics. So what did we learn? It was the important thing is when the policy evolves, okay, when you look at these rollouts, your initial rubrics no longer work here. So you need to keep improving your rubrics, right? Now there are new judgments that need to be added to evaluate how good one response is from the other, okay? And that was the main idea here, which is now we have evolving rubrics that improves when the policy improves, okay? So this is the algorithm. We have our training data. The query comes in. The policy gets updated. We generate responses. And now, looking at these different kind of generated rollouts, we have a judge model that generates rubrics such that it discriminates better between these responses. And then for given queries that we have, now we compute the kind of linear weighted sum of those scores, okay? And we keep updating the buffer of rubrics that we have because some of those rubrics are becoming useless, and then we remove. Yeah.
The judge also trained at the same time as the policy?
I was expecting to ask, someone asked this question. No, judge is actually a very strong model. I think here it's like GPT model, which is very expensive. And when I want to talk about limitations, I want to talk about that problem. We assume that this judge is like a really good judge model. And when we used an out-of-the-box smaller model, like I think either OLMo 32B or Quen 32B, just by prompting, it didn't work. Now we are kind of trying to train this better judge model. That is definitely the weakness, I agree. Cool, so this is how the process looks like. We automatically generate rubrics for the initial query. Since we are focused on deep research, especially a lot of initial rubrics are based on like search accuracy. Then we roll out, we generate multiple rollouts. Then we generate multiple rubrics, update our buffer, update the new reward, and then update the buffer, maybe mostly by removing some of those rubrics. Okay. One other important thing again here was we need to cold start our training. So we needed to add high quality SFT data to make sure that like the model is capable of searching, and then we apply our RL method. Okay, so results are actually very good. So I'm very happy and excited to see this. So first of all, this pink model, we've evaluated it on scientific question answering, I don't remember what, and then health bench. This is, I forgot the name. Deep research benchmark, some other deep research benchmark, and then health bench. So our model is better than other open weight deep research methods on these. And to our surprise, it was also very much similar to like proprietary deep research models, especially when we released this model, DeepMind, Gemini 3 deep research came, and like we are pretty much better. We have a little bit, a slight advantage on the scientific QA because we had access to expert rubrics at the beginning, so it was better. But even in other benchmarks, we saw the improvement, which was very interesting. So another argument here was this is the graph for score versus the cost. Like 10 queries cost like 2 cents or less when we, like assuming we calculate the cost of serving GPUs. And then like obviously it is much more expensive if you use one of these closed models. Now, the big question is, do I argue that you should use Dr. Chulu instead of any deep research type search instead of like Gemini type model? My answer is no. But the argument I'm making here is you can, if you have domain knowledge, you can specialize models for your task. And we don't need to have this like super gigantic, very expensive generic model for every single task that we are interested in. And we could build a specialized model, which are going to be much cheaper. And I think a lot of companies now are moving in that direction. Okay. Oh, this was also very interesting and surprising. We had some collaborators in medical field, and they were kind of trying to do these genetics documents analysis and so on, and then pretty much out of the box, the model worked on their setting as well. Here are kind of the numbers compared to GPT-5 models, like pink versus gray models. Okay, good. So I want to end this talk. To summarize, I talked about pre-training, post-training, the basic models, and then how to expand it beyond just RLVRs and how to get to more complex tasks. So we've released a few models in post-training and pre-training. We are very excited to see people are using our models. So I have research academic background, and I was very surprised to see that actually these models are being downloaded and being used. So very exciting. We have done some analysis on how people are using these models. These are kind of different types of tasks. A lot of it is kind of how to look at the data quality, what is the role of data in some of these pre-training settings. This is up to OLMo 2. I don't have these analysis for OLMo 3. Some people are looking at training dynamics. Some are looking at using these models on like developing new hybrid architectures. And yeah, that's pretty much it. So I'm gonna stop here and talk about one more point here, which is I believe I also mentioned this at the beginning. For building all these models, we are making a big assumption that data access is binary. Either data is public or private. We train on public data and we cannot train on private data, okay? However, data comes at different stages. Some company might let you use your data, but then later they would say, okay, opt out, okay? So we need to have some training setting that enables opt-in and opt-out of the data. So it's important, and then don't say, okay, now I have to retrain from scratch, right? If I could say, I'm gonna extract this data and the effect of this data from my weights have decreased, this is very important. So we have some model called lifecycle that tries to approach that. I really encourage all of you to also think about this problem, how to think of new paradigms that are modular enough and enables different types of access of the data. Okay, thank you very much. And I want to finish with this. Oh,
A few questions.
yeah, thank you. Yes.
That's kind of question. But how do you? I mean, this is a concern that like a lot of the things we have in this open source domain, they're basically taking a lot of information from big models. And on top of that, like it's like doubly bad if we're getting it from and stuff like that. And almost certainly, like they've like have information. Probably.
Yeah. Yeah.
So how do you think about this in terms of like the benchmark number?
Yeah. Very good question. I want to say I have two answers here. One is I believe in open source we pretty much know the whole pipeline of the frontier models. Better engineering, better infra, better resources still exist, but the process is pretty much the same. Okay, so this is, and I believe according to like everything that a lot of people have worked on, we are on the same ballpark. Two, different groups are interested in solving different problems at the different stages, and they could start thinking, I'm running out of data, okay? How can I think of better way to generate synthetic data that doesn't rely on a teacher model but I could improve my model, right? So this is kind of one group of research question. I don't think even big labs have solved it. So having access to these different checkpoints would enable that. There are other groups that think I need to think of the next version of building best model. So let's build on the best open source model that is available. Agree, some reasoning traces are distilled from these bigger labs or so on, but those bigger labs use expert data annotated by human. So we are kind of distilling from them. But now I'm thinking about the next generation of problems that we don't have good solution. Like, for example, these evolving rubrics, and so I chatted with multiple people, they also don't have good solution, right? So we can, as a community, now that we have these tools available and these kind of open models, with a little bit of maybe cheating, I mean, at some levels, we could start thinking about the next level of these problems. So I want to be, like, I think these are all very valuable because it enables doing research at different stages of training. But I resonate with what you're saying. Yes.
Not for the talk. So I was just kind of wondering if you could give like what was the magnitude, how many flops are thrown in each of these like the stages of pre-training, mid-training, and the post. Yeah,
that's a good question. Let me add one more thing to Sham's answer. However, I want to say we need to be very careful about interpreting results. So probably you've seen some of our earliest results on like how we were seeing some very weird behaviors with like Quen models. So it's important to question every step also at the same time. Sorry. So I don't exactly know the training file, but I can tell you exactly the numbers of training. So for pre-training, we train on 6 trillion tokens, same size. Mid-training, we train on 50 billion tokens. Long context, either 50 or 100 billion tokens. Post-training, significantly less. We didn't even calculate the number of tokens. I think it was more like number of training instances that we used. So it was like 2 million training instances, which is like 2 billion token or a little more, yeah. But everything like it gets discrete. But yeah, that is kind of the way you would think. Yes.
You mentioned this incident where you had this model like kind of accidentally specialized to Amy and then the one sets of results. What was like the how did you fix that?
Yeah, it was very interesting. It was very interesting finding. So the model became really good at Amy. It was for every single question, even like, hi, how are you? Tell me a joke or something. It was doing a lot of long reasoning traces generation because it had learned that I have to do reasoning for every single task too, and it was hallucinating a lot because it had learned it's okay for me to connect a lot of pieces of information. And then we first thought it's because of a lot of extra steps that we've done in RL, went back, no, and then moving back, we finally realized it's because of our SFT data. In our SFT data, we had a chat, a lot like that chat from Wild Chat, which is like general type chat that people like we collected. And we noticed that the data was noisy. The model pretty much learned that it is okay to do chain of thought reasoning and then have a noisy response. So the way we approached that, we started doing a lot of filtering to remove that noisy data. And have like only very high quality data, even if in chat, and then decrease the amount of chat data that we had. And then it improved. Because it's a well-known problem that in general, the model that are better in thinking, their hallucination and factual incorrectness increases. So it is the case, but then now it is not dramatic. Back then it was like dramatic. But we realize, again, quality of data is really important. Yes?
All the team has put in a lot of effort into but I wonder if you've looked into how data curation, the data that you're going to need for readers, whether the same appearances that you mentioned happen across the.
Yeah, we've definitely looked at it a lot in post-training because it is cheaper, and definitely like our SFT stage is very cheap. We've done many iterations. So we've collected a lot of information that way. But we've noticed that we really need to have a strong model for reasoning before passing it to RL, such that RL can pick up, okay? But at the same time, this instance that I described, where we had noisy SFT data, which we weren't that careful about one particular domain, it really caused bad issues for us during the RL stage. So we've done a lot of this study here. But all of this narrows down for us, like this is the next iteration that we are doing, which is how we improve our evals, our evaluation benchmarks, such that these things don't happen. Then, like it is already built during the process. Okay. Mid-training to SFT, we've also done this evaluation. In general, we've noticed that the higher we get to our mid-training, that checkpoint is usually better for the SFT stage. But again, given our benchmarks, there might be other benchmarks too. From pre-training and onward, these are very expensive. We haven't done that. Thank you.
Thank you, Hanna, again.
Thank you.
Thanks.